Hi everyone, I'm Uma. I'll be telling you about a result on eliminating intermediate measurements using pseudorandom generators. This is a joint work with Ranras. I'll begin by giving you a preview of our results and then go on to describe the background and motivation for our results. So here are our results. Our first theorem is that quantum algorithms with unitary operators and intermediate measurements can be simulated by algorithms with only unitary operators and without intermediate measurements using very little overhead in time and space. More precisely, if our original algorithm was of time t and space s, we show a simulation in time t poly s and space s log t. In other words, we give a version of the principle of deferred measurements that is both space efficient and time efficient. Our second result is that we show pseudorandom generators for space-bounded quantum computation. We consider quantum algorithms that can read classical random bits, and we show that a variant of the INW generator fools such quantum algorithms. Now let's move on to the background behind these results. Let's start with what are quantum algorithms of time t and space s. Essentially, for us, a quantum algorithm of space s and time t is a quantum circuit with s qubits and t operators. So there are s qubits initialized to the 0 state, and there is a sequence of t operators. What kind of operators are allowed? So this is a fundamental question, and based on the kind of operators that we allow, we could get potentially different models of computation. So first we have the unitary model of computation, which we are most familiar with. Here we fix a set of gates, unitary gates, that is universal for quantum computation. For example, we fix the Hadamard and Toffoli gates and look at circuits that are built using these operators. This is what we call the unitary model. Consider a model that can apply these operators and can additionally apply measurement. So these are algorithms where you can perform measurements during computation. We call this the unital model of computation. Finally, we have the most general model of quantum computation, where in addition to these unitary operators and measurements, you can apply a reset operator. So what is a reset operation? This is an operation that takes a qubit in an arbitrary state and maps it to the 0 state. Equivalently, it discards that qubit and gets a fresh qubit initialized to the 0 state. Another way of thinking of these general algorithms is thinking of them as hybrid classical quantum algorithms. So these are algorithms which have both quantum memory and classical memory. On the quantum memory, you can perform unitary operations and measurements. On the classical memory, you can perform classical operations, including erasure operations. And there is some limited interaction between the quantum and classical part. So this is the most general model of quantum computation. Turns out that this reset operation is quite a powerful operation in the sense that using the reset operation and the Toffoli gate, you can simulate a measurement. So for the rest of this talk, we're going to be ignoring this model of computation and focusing only on the unitary and the unital model. So for us, a quantum algorithm can only apply Hadamards or Toffoli gates, or in some cases, perform intermediate measurements. There is a technicality here that I have not talked about, which is how does the input and output enter the picture? Typically, algorithms have an input and they produce an output. So the way the input and output enter this picture is as follows. The input is what describes the quantum circuit. More precisely, we require that there is a classical log space algorithm, which on input X outputs a description of this quantum circuit. Namely, it outputs the sequence of operators and which qubits they act on. The output of the circuit is defined as follows. We fix a subset of qubits and measure them at the very end of computation. This results in a probabilistic string, and we declare that as the output of a quantum circuit. For the rest of this talk, we can ignore this issue of inputs and outputs and simply work with quantum circuits with S qubits and T operators. Here is an example of a quantum circuit of space 5 and time 9. I'm now ready to state our main problem of interest. Given a quantum algorithm with intermediate measurements, can be simulated by a quantum algorithm without intermediate measurements. Are algorithms that can perform intermediate measurements more powerful than algorithms that can only perform unitary operators and no intermediate measurements? Does the ability to perform intermediate measurements give more power to quantum algorithms? This is a really fundamental question in quantum computing about the relative power of algorithms that can make measurements as opposed to algorithms that cannot make intermediate measurements. This question has applications to other areas, for example, reversibility of computation. Can we simulate the irreversible operation of doing a measurement by using some reversible operations in a space-efficient and time-efficient manner? This problem is also interesting with regards to error reduction, since space and time-efficient error reduction is known for reversible algorithms, but not for irreversible algorithms. So what do we know about this question? One very basic principle in quantum computing is the principle of deferred measurements. So this states that the following two quantum operations are equivalent. On the one hand, you have a measurement of a qubit. On the other hand, you are copying this qubit onto a fresh qubit and ignoring that fresh qubit for the rest of the computation. The principle of deferred measurements says that these two operations are equivalent. So instead of measuring a qubit, you can copy it onto an ancillary qubit and ignore that ancillary qubit for the rest of the computation. Effectively, these operations are the same. This implies that quantum algorithms of time t and space s with intermediate measurements can be simulated by algorithms without intermediate measurements in time t and space s plus t. So why is there an s plus t? Well, the original algorithm could perform potentially t measurements, and to simulate each of these measurements, we need a fresh qubit. Note that S could be polylogarithmic in T, and in this case, the blow-up in space is exponential. Hence, the principle of deferred measurements gives a time-efficient way to defer measurements, but it is not a space-efficient way. So one can ask, is there a space-efficient way to defer intermediate measurements? This was an open question until very recently. It was resolved by these two independent works that indeed you can defer intermediate measurements in a space-efficient manner. So if your original algorithm had time t and space s, then your new algorithm has space s plus log t and time polynomial in t and 2 to the s. Typically, s is at least log t, so the blow-up in space is constant. However, when s is much larger than log t, think of s as polylog t, but much larger than log t, then the blow-up in time is quasi-polynomial. So this is not a time-efficient way to defer intermediate measurements. So these were the state-of-the-art results. With regards to our open question, the best simulations we knew required either an exponential overhead in time or an exponential overhead in space. So one can ask, is there a way to defer intermediate measurements that is both space efficient and time efficient? This is the question that we answer. Our main theorem is that we can indeed defer measurements in a space efficient and time efficient manner. More precisely, we show that quantum algorithms of time t and space s with intermediate measurements can be simulated by quantum algorithms without intermediate measurements in time t poly s and space s log t. So we give a version of the principle of deferred measurements that is both space and time efficient. For example, this implies that quantum algorithms of polylogarithmic space and polynomial time don't require intermediate measurements. So this is our first result. I will now begin describing our second result. But before that, I'll describe the connection between our first and second result. And the connection is the following. The connection is the observation that intermediate measurements and randomness are equivalent. What do we mean by that? First, intermediate measurements can be used to generate perfect randomness. Consider the following circuit. You have a qubit in the 0 state, apply a Hadamard operator, and then a measurement gate. The measurement outcome is going to be 0 with probability half and 1 with probability half. So the measurement outcome is a uniformly random bit. To generate more random bits, you could apply this Hadamard and measurement gate over and over again, and the sequence of measurement outcomes would be a sequence of independent uniformly random bits. Thus, intermediate measurements can be used to generate perfect randomness. Interestingly, the other direction also holds. So randomness can be used to simulate intermediate measurements. So how do we do this? We show that the following two circuits are identical. On one hand, you have the measurement of a qubit. On the other hand, you have a controlled unitary. The unitary is basically the reflection about the one state, and the control is on a uniformly random bit. By this, we mean a quantum state, which is with probability half in the 0 state and the probability half in the 1 state. So these two operations are equivalent. The proof of this is quite simple. It involves writing out what the action of each of these circuits is on the basis states and checking that they're equal. So this implies that intermediate measurements and randomness are equivalent. Thus, given any quantum algorithm of space S and time t with intermediate measurements, we can write down an equivalent quantum algorithm of space S and time t without intermediate measurements, but with read once access to a sequence of up to t uniformly random bits that are independent. Therefore, the problem of eliminating intermediate measurements is equivalent to the problem of removing random bits for a quantum algorithm. In other words, the problem of derandomization of quantum algorithms. The idea is that we can hope to replace the t uniformly random bits of this new algorithm by t pseudorandom bits. That is, t bits which contain very few truly random bits, and the rest of the bits are a function of these few truly random bits. This naturally leads us to the concept of a pseudorandom generator. So now let me describe what a pseudorandom generator is. A pseudorandom generator is a function which stretches little t bits to capital T bits. Think of little t as much smaller than capital T. The input of the generator is called the seed, and the length of the seed is called the seed length. The property we want of a pseudorandom generator is as follows. Consider the ideal case when we have a space S time t algorithm F, which takes in capital T uniformly random bits and outputs something. Consider another case where we have the algorithm F, but instead of feeding it capital T uniformly random bits, we take little t uniformly random bits, apply a generator G, which stretches these little t bits to capital T bits, and we feed these capital T bits to the algorithm F and look at the output. The property we want of a pseudorandom generator is that these two outputs are similar. In other words, we want to mimic the behavior of the algorithm F on a large number of random bits by its behavior obtained by taking a few number of random bits and stretching them using a pseudorandom generator. More formally, a pseudorandom generator has the property that the final state of the algorithm, when the random bits are drawn from the output of G on a uniformly random seed, is close to the final state when the random bits for the algorithm are drawn uniformly and independently. By close, we mean epsilon indistinguishable in the sense that the difference between these two final states is at most epsilon according to some norm, typically the L1 norm. So as an equation, this is how we would write it. So let f of r denote the final state of the algorithm on a random string r. We want the final state f of g of x, where x is drawn uniformly at random from 0, 1 to the little t, to be close to expectation of f of y, where y is drawn uniformly at random from 0, 1 to the capital T. So this is what a pseudorandom generator is. The parameter we're trying to optimize here is the seed length. We're trying to minimize the seed length of the generator because we're trying to simulate the behavior of the algorithm on a large number of random bits by using as few random bits as possible. I'm now ready to state our main result. Our second main result is that we show a pseudorandom generator for quantum algorithms of space S and time t with access to a read-one step of random bits. So the INW generator is a classical pseudorandom generator. For time t space S algorithms, it uses seed length S log t. It is also computable in very little space and very little time. We show that a variant of this generator actually works for quantum algorithms of time t and space S, which read random bits. This result also holds for algorithms that can reset operations. To the best of our knowledge, such kinds of PRGs for quantum algorithms that can read random bits have not been studied before, possibly because in most settings, quantum algorithms can generate perfectly random bits. But this relies on them being able to perform intermediate measurements. We think this concept of pseudorandom generators for quantum space-bounded algorithms that read random bits is interesting in its own right. One reason it's interesting is, of course, the connection with eliminating intermediate measurements that I already described before. But we think it might be interesting from other perspectives. For example, PRGs provide an example of a distinguishability task that small space quantum algorithms cannot solve. So the problem of distinguishing a truly uniformly random string from a pseudorandom string is something that small space quantum algorithms cannot solve. And this is interesting from a complexity theoretic perspective. PRGs for quantum algorithms reading random bits are also interesting in the setting when the quantum algorithm cannot be relied on doing what it's supposed to do. For example, you could have a protocol where the quantum algorithm needs to toss a large number of random bits and perform some operation based on them. Suppose you cannot guarantee that the quantum algorithm is indeed tossing truly uniformly random bits. How do you ensure that the algorithm behaves as it should behave? Well, if you cannot toss those random bits yourself, a pseudorandom generator might be a way for you to ensure that the quantum algorithm is indeed behaving as though it had tossed uniformly random coins. Another reason we think PRGs are interesting is that it quantifies how much randomness is truly necessary to simulate a quantum system. So these are settings where we think PRGs might find applications. But of course, our main application is in the problem of eliminating intermediate measurements. So now let me talk a little bit about the proofs of our results. First, I'll start by explaining this connection between PRGs and eliminating intermediate measurements more clearly. I already described it, but I'm going to give more detail now. So let's start with an algorithm Q with T intermediate measurements. How do we defer these T intermediate measurements in an efficient way? First, using the equivalence between measurements and randomness, we write down an equivalent quantum algorithm Q prime that has no measurements, but uses T random bits. We then use our pseudorandom generator to replace these T uniformly random bits by T pseudorandom bits, which contain only S log T truly random bits. This incurs only a small blow up in the running time and a small error. We then again use the equivalence between measurements and randomness to replace these S log t truly random bits by S log t measurements. Finally, we defer these S log t measurements using S log t additional space. This is just the classical principle of deferred measurements. So this is how, using PRGs, we take an algorithm Q with t intermediate measurements and simulate it by an algorithm with an additional S log t space, with a small blow up in runtime, and with no intermediate measurements. Now let me describe some of the ideas behind our construction of the pseudorandom generators. So here is our main lemma. Given any quantum algorithm of time t and space s, which reads t random bits, we use B of R to denote the final state of the algorithm on a random string R. Let G be a variant of the INW generator for space S time t classical algorithms. The seed length of such a generator is S log t. We show that the average final state B of R, when R is drawn uniformly at random from 0, 1 to the capital T, is close to the average final state B of G of R, when R is drawn from the uniform distribution over 0, 1 to the little t, and G is the INW generator I just mentioned. So this is what we want to show. I'm not going to describe the INW generator, but I'm going to give you some ideas behind the construction of this INW generator. I begin by describing the classical motivation behind the construction of the INW generator, and then show how it generalizes to the quantum setting. The idea is as follows. We think of the algorithm B, which is now classical. We think of it as a function taking a uniformly random string y over capital T bits and an initial state, and outputting a final state. So initially you have the all zero state. The algorithm reads y1 and updates the memory. The algorithm reads y2 and updates the memory, and so on. And finally, the last state of the memory is declared as the final state of the algorithm. Now consider the midpoint of this algorithm and divide it into two equal parts. So let B0 be the first half of the algorithm and B1 be the second half of the algorithm. So now B0 is an algorithm that takes a uniformly random string y over t over 2 bits and outputs a final state. This final state is defined to be the initial state of B1, the second half. So B1 now takes a uniformly random string y prime over t over 2 bits that is independent of y. Here is the main observation. The only information that is passed from B0 to B1 is the state at time t over 2. And this is a state on at most s bits. Therefore, the amount of information that B0 could leak about the string y to the program B1 is at most s bits. So one could hope that instead of using y and y prime that are completely independent of each other, we might be able to get away with using y and y prime that are correlated by means of an extractor. So here extractor is a suitable function, which I will describe later on. It acts on the string y and a few additional random bits and produces an output. And the idea is that instead of using y prime, we would use the string extractor applied to y comma d, where d is a uniformly random string over a much smaller universe. For us, d will actually be a string on roughly s bits. So what this does is effectively reducing the randomness from t to t over 2 plus roughly s. The idea behind the INW generator is to recurse on this construction and intuitively recursing log t times, each time incurring a seed length of s, we would overall get a seed length of s log t. So this is the intuition behind the classical INW generator. To generalize this to the quantum setting, we make use of a quantum extractor. So let me describe what a quantum extractor is for our purposes. Imagine a setting where Alice has a uniformly random string y and Bob has some information about Alice's input. So he's allowed to look at Alice's input and write down some information. So by this, we mean a quantum state rho y consisting of t qubits. So now Alice's and Bob's inputs are correlated. Now apply a quantum extractor on Alice's input using some additional random seed S. So this modifies Alice's input. And the property we have of an extractor is that after the application of the extractor, Alice's and Bob's inputs are nearly uncorrelated. So if you look at the final state of Alice's and Bob's input after application of the extractor, it looks almost like a tensor product state. It behaves as though Alice had a uniformly random string y prime and Bob had a uniformly random row y, where y and y prime are independent. So an extractor injects few bits of randomness into Alice's input so that the resulting input of Alice is uncorrelated with Bob's input, almost uncorrelated. So such objects have been studied. We make use of a quantum extractor from the result of Fer and Schaffner. So they show that if Bob could store at most t qubits of information about Alice's input, then you only need to inject roughly t bits of randomness into Alice's input. So this is the quantum extractor that we use to generalize the INW classical pseudorandom generator. So this completes an overview of the proof. Let me summarize. We showed two main results. Our first result is that quantum algorithms with unitary operators and intermediate measurements can be simulated by algorithms with only unitary operators and without intermediate measurements, using very little overhead in time and space. More precisely, if our original algorithm had time t and space s, then our new algorithm has time t poly s and space s log t. In other words, we give a version of the principle of deferred measurements that is both space efficient and time efficient. Our second result is that we show pseudorandom generators for space-bounded quantum algorithms that read classical random bits. We show that a variant of the INW pseudorandom generator actually fools such small space quantum algorithms. This brings me to the end of my talk. Thanks for listening.